Hello everyone, hope you are doing great, and in this video's lecture I'll be talking about retrosynthesis. Previously I finished the complete chapter of Claydin retrosynthesis. That was a 1 hour long video, approximately 65 minutes. If you haven't watched that video, please watch. And if you are a beginner in terms of retrosynthesis, that is the first video that you should watch. And there are quite few other videos that are present in the playlist of retrosynthesis, so please feel free to watch those videos before in going through this video lecture, because this is a little bit advanced level, because I will not be introducing the basic terminologies of retrosynthesis and how to do disconnections. So this is a more of an exercise and an example that how retrosynthesis can be used to prepare long complex big molecules having multifunctional groups. So it's more kind of a MPhil or PhD level, master's level in this video. And if you are a beginner at college or university like BSc level, please watch that video of mine where I have completely introduced the retrosynthesis from the Claydin book using the chapter 30 of his book. Okay, let's look at the first example of this video lecture. This is a compound, as you can see it, you are asked to do retrosynthesis of this compound. So there are two possible disconnections, disconnection A and B. So if you look at the synthesis of this compound before going to the retrosynthesis, so you can start the synthesis of this compound from this aldehyde and using this triphenyl phosphine and this Michael acceptor, you can prepare alkenes. So it's kind of a Wittig reaction. So this is a Wittig reaction. The starting material is aldehyde and triphenyl phosphine is this. So you have alkene, and now you have alpha beta unsaturated. No, not alpha beta. So you have a conjugated system of having alkene benzene ring and ester group. Now you can do condensation reaction. Like this ethoxide is a base. What it will do, it will take proton from one of the acidic hydrogens, probably from here, because this is most acidic, and generate a negative charge, and that will attack on this ester or this double bond, and it will give you a cyclized product, 6-member ring. And then in the next step we will look into the mechanism of these reactions in a separate video lecture series, where I will be introducing the mechanisms of every important organic reactions, starting from simple reactions to going to complex reactions. That is our separate playlist. So in this video we will be focusing on conversions, reagents, preparation of the molecule, rather than going deep into the mechanistic insights. But if you have any questions regarding mechanism of any of the reaction, please drop your comments in this video. I'll try to explain the mechanism in the next video. Okay, then now you have this 1,3-diketone functionality. What you do in number 1, reduce it by using any reducing agent, say for example sodium borohydride, and then you do alkylation using lithium reagent from methyl iodide. So you will alkylate the ketone by using a methylation procedure, and in the next step it's kind of imine formation and then cyclization to get the desired product. So this is a cyclic amide, so, and this is a cyclic alkene and benzene. So this is how you can prepare the complex molecules. And now if you have to do retrosynthesis of this compound, how will you do it? So you can go from this compound back to the compound 2. So you can disconnect the bonds accordingly. As you can see, this is the synthesis of this compound. So you should know both ways. You can either go from synthesis to the retrosynthesis and from retrosynthesis to synthesis. So you must know how to go forward and how to go backward in order to be very good at retrosynthesis. Okay, let's move on to some other examples, some other chemistries which are related to synthesis particularly. So for example, if you are doing retrosynthesis of this compound And what you need to do really is you have to break this compound into two fragments, and the one fragment is going to be an electrophile which will contain a positive charge, and another fragment is going to be a nucleophile which is going to contain a negative charge. This is the basic retrosynthesis. When you are going to break a bond between two atoms, one is going to acquire a positive charge and another will get a negative charge. Then you have to supply synthetic equivalents for these charges. Now this negative charge on carbon, the reagent that it will be equivalent for this is active methylene compound CH2 having esters on both sides of this unit. What ethoxide will do is deprotonate one of the CH2's hydrogen, will generate a negative charge like this, and this negative charge will attack on this electrophilic center like this. Is a SN2 reaction, primary alkyl halide undergoing nucleophilic substitution reaction to give you the target compound, this one. So this was very simple example of retrosynthesis, just to recapitulate that how retrosynthesis works basically. So you disconnect a bond. Again, I'm repeating how retrosynthesis works. You disconnect a bond, you will get two fragments. One fragment will get a positive charge and another will get a negative charge. Now you have to supply reagents for positive and supply reagent for negative charge, and then you do the reaction. Okay, let's move on to the next example. This is a retrosynthesis of a DiolsAlder reaction. So whenever you see cyclized compound, you must give a thought to using DiolsAlder strategy. So it's a cyclization reaction. It's concerted. It undergoes via concerted mechanism. So these are the three arrows that you should remember how to point them out. So this double bond goes toward there, and the bond between these carbon and carbon breaks and shifts toward this side, and this arrow moves towards this end, and you have diene 1,3 butadiene and ene. So these are the two basic substrates, I would say, that are required for DiolsAlder reaction. So you react ene with 1,3-diene to get your desired product. Now 1,3-diene reacts with ene in this way to give you the product. So now the purpose of showing you this example is that when you are doing retrosynthesis of complex molecules where you have this unit having an alkene in a cyclic ring and double bond in a cyclic ring, and then other functional groups on the side chains. So you must think of this strategy that you can prepare cyclic alkenes by DiolsAlder strategy. So hope you understood this concept, and let's move on to the next part. Again, this is a DiolsAlder reaction, but it's in a bicyclic system, which sort of a thing where you have oxygen bridge here, and then you just do what you have to do in DiolsAlder reaction. Move around the arrows from one position to another and come up with 1,3-diene and ene. Like for example, this is furan type ring, and you have a 1,3-diene there inside the ring. It doesn't matter it's a cyclic 1,3-diene or acyclic 1,3-diene. As long as it's 1,3-cyclic diene, it's fine. Then you can react this 1,3-cyclic diene to get your desired product with suitable ene. So these two reagents, aldehyde and this furan, react together and they will give you the product. This was another example of DiolsAlder strategy where you can use this DiolsAlder approach to prepare these sort of compounds. Okay. In this slide, you will learn the disconnections of simple alcohols, and you should remember these strategies, or you should understand these sort of approaches when you will solve the complex molecules, because they will come handy there, because you will be familiar already that how you can disconnect these compounds. So for example, this is cyanohydrin. It's an alcohol and it's a tertiary alcohol, so you disconnect this compound from this position, and one will get a positive charge and another will get a negative charge. So the positive charge will be called electrophilic center, and the negative charge will be called nucleophile. So when you will react these together, cyanide will act as a nucleophile and it will take on this carbon. You will get this compound. But the equivalent for this positive charge will be ketone, because when ketones react with cyanide nucleophile, you get to the product that is cyanohydrins. Now another example of this retrosynthesis is this one. So this is a forward direction reaction. You are starting from acetone, it's a ketone compound, you are reacting with sodium cyanide in acidic medium and you get cyanohydrins. That's your desired product. And this is how you do disconnection of alcohols. So it was a good strategy that you can prepare cyanohydrins or tertiary alcohols containing cyanide functionality, starting from ketones or aldehydes having reagent called sodium cyanide as a nucleophile and acidic conditions to do the job. Let's move on to the next example. Again, this is an alcohol which is a tertiary alcohol, but instead of cyanide we have alkene functionality. So sorry, not alkene, alkyne. Now it's similar to cyanide, it will act as a nucleophile and we will have a ketone instead of this alcohol. Now you got this ketone. Now you have alkyne which contains a negative charge. As you are very familiar with these alkynes, that the alkynes contain 2 CH units which are acidic in nature. So what I mean by acidic is that the pK value of these alkynes is pretty much low and they can be deprotonated with a strong base such as sodium and liquid ammonia to generate a negative charge. That negative charge will act as a nucleophile, and in this way you can make the CC bond connection, not disconnection but connection. So this negative charge will take on the carbon of ketone and then you will have a bond between carbon and carbon, and this is how you can prepare carbon-carbon bond formation starting from alkynes and using ketones. Then you will get the tertiary alcohols. This was another approach where you can prepare alcohols if you have alkynes next to alcohol. In last example we saw that we have alcohol but next to that alcohol was cyanide. In this example, instead of cyanide we have alkyne, which the purpose and the role of cyanide or alkyne is basically the same. They will act as a nucleophile. Okay, let's move on to the next example. This is tertiary alcohol. It's time to practice now. Another strategy for alcohols is that you can use a Grignard Reagent strategy to prepare alcohols. So you need to first understand that what type of alcohol it is. Is it primary, secondary or tertiary? Then you disconnect accordingly. So in this case you have a tertiary alcohol. The disconnection will be straightforward. One side will become ketone and another side will become the Grignard reagent. So when you will react this Grignard reagent with this ketone compound, you will get the tertiary alcohol. Okay, it's example again. You have a tertiary alcohol, but the difference in this compound is that you have 2 similar side chains, that is ethyls. So what you can do is either you go from ketone to ester by disconnection, or you can disconnect both ethyls at the same time and make one part ester, and then the next part becomes Grignard reagent. So for example, this is ester now. If you are reacting this ester with Grignard reagent, you will get the alcohol. So this is how you can prepare alcohols starting from Grignard reagents. So this was a trick that you can use, that if you have tertiary alcohol and the side alkyl chains are similar, means ethyls like in this case, then you can start from ester, and then you can use the 2 equivalents of ethyl magnesium bromide to get your product. Now this is tertiary alcohol again. You can use this same strategy as previously told you, that now in this case you have 2 similar sort of situation in where you have 2 alkyl groups. Then you can disconnect these alkyl groups, not alkyl in this case, but 2 phenyl groups rather than ethyls. We have 2 phenyls, then you can disconnect 2 phenyls, the rest of the compound will become ester, and then you can react this ester with phenyl magnesium bromide, and then you connect these 2 compounds together to give you the product in the forward direction. So what we are doing here is we are learning how to do disconnections when we have alcohols. So we have discussed that if we have cyanide next to alcohol, we have discussed alkynes next to alcohol, and now we are doing the Grignard reagent approach for alcohol retrosynthesis. Okay, let's move on to the next example. This is a DiolsAlder situation where you have double bond inside the ring. Now you have to move around those arrows and generate the 1,3-diene, that is called 1,3-butadiene, and ene functionality. Now you react these two together to get the desired product. This is how DiolsAlder reaction works. No reagents are usually required for DiolsAlder reaction. Just mix these 2 substrates, A and B. A should be 1,3-diene and B should be ene. Then you mix A and B to get the final product. Now if you have the double bond inside the ring and alcohol outside the ring, then how you are going to do retrosynthesis? What you need to do is to do FGI, convert the alcohol into ester, and then do the DiolsAlder reaction. Then do the DiolsAlder disconnection. So what I mean by this is you can connect 1,3-butadiene with ene to give you the cyclic alkene, double bond inside the ring, and then you can reduce this ester using lithium aluminum hydride as a reducing agent to give you the primary alcohol. So just little bit tweaking, just little bit changing the situation, but it's still the strategy, still the big approach is same, where you have a double bond inside the ring. Okay, let's move on to the next example. This is just the summary, quick summary that how we can use alcohols to prepare wide variety of functional groups. So for example, if your starting material is alcohol, and if you are reacting with some sort of halogens like phosphorus bromide or phosphorus iodide, then you can prepare alkyl halides directly from alcohols. And if you can do oxidation of alcohols, then you can either get aldehydes or ketones depending upon what type of alcohol it is. And then if you treat alcohols with strong acids, then you can prepare ethers. And if you do oxidation like harsh conditions or strong oxidizing agents, then you can prepare carboxylic acids as well, but it should be a primary alcohol if you want to go towards carboxylic acid, because initially the alcohol will be oxidized into aldehyde, and then aldehyde will be oxidized into carboxylic acid. The next reaction that alcohols can undergo is etherification or ether formation and elimination as well, where you can prepare the, by the way, I'm using this Stuart Warren book in this video lecture, and I have prepared these slides from that book, and this is a very good book for retrosynthesis, and it summarizes everything and provides a lot of practice examples. So if you have that book, then yeah, you can refer to that book, or if you need it, then I can send it to you. Drop your email in the comment below. And elimination, alcohols can undergo elimination reactions to give you the alkenes. So that's the main important reaction that alcohol can undergo, and you can summarize from this, you can summarize the knowledge, or you can summarize the outcome of this slide is that we can prepare alkyl halides, ethers, alkenes, carboxylic acids, aldehydes, and ketones from alcohols by using different reactions. Okay, let's move on to the next slide. Now in this example you don't see alcohol, but if you see closely, you can convert the starting compound, like target molecule, by using FGI ester. This is acetyl group. So you disconnect this acetyl group, one part will become carboxylic acid and other part will become alcohol. Now you have this alcohol and the both sides are same. Okay, so this is symmetrical alcohol, I would say, where you have two similar sides. Now you can disconnect these two sides and you can have ester as a starting compound and Grignard reagent strategy. So in order to prepare Grignard reagent, you should start from alkyl halide, then react Grignard reagent with magnesium in the presence of diethyl ether, and react this Grignard reagent with ester to give you this alcohol, and then convert this alcohol into acetylating reagent, or this step is called acetylation, introduction of acetyl group, to give you the target molecule. So this was another example where you just need to think a little bit. Like in first step you just disconnected the acetyl thing to generate the alcohol step, and then you are straight away you can identify it's a tertiary alcohol, and then you can disconnect both side chains which are very similar and start using the Grignard reagent strategy to prepare tertiary alcohols starting from esters. Okay, let's move on to the next slide, and this is again a learning slide, not examples. We will do more examples in later on in this video. First we are learning the techniques, we're learning the strategies, we are trying to learn the tools. We should have a toolkit in order to use our tools to prepare complex compounds using this strategy. So you have alkyl halide, what you do is to FGI, that is functional group interconversion. You convert alkyl halide into alcohol, and then you disconnect the CC bond between this alcohol. The one side becomes Grignard reagent and the other side becomes the aldehyde. This is one way to do disconnection of these alkyl halides. But how about the disconnection of these primary alcohols? You can disconnect these primary alcohols from this carbon phenyl bond. It doesn't necessarily to be phenyl, it could be R group, anything. So you disconnect from this position, the one side becomes phenyl magnesium bromide and the other side becomes this positively charged xanthone, which will be equivalent to epoxide, because you can see this oxygen is a nucleophilic in nature and this carbon positive charge, they are very near to each other, in proximity to each other, and this oxygen will attack on this carbon to give you the epoxide ring. Now this phenyl magnesium bromide will attack on this epoxide ring, and the ring opening will take place and you will get a negative charge, and if you react this negative charge with water, then you will get the alcohol. So this is another way to do disconnection of alcohols. And last step is also summarizing that how you can use Grignard reagent for the ring opening reaction of alcohols. For the ring opening reactions of cyclic ethers. Epoxides are basically cyclic ethers. They can undergo ring opening reaction to give you the alcohols. Okay, let's see how you will do in this example. You have an epoxide and you are reacting this epoxide with Grignard reagent. What will you get? You will get alcohol on one side and alkyl chain on other side. So this is the purpose of this slide, is to show you that you can extend the carbon-carbon chain or carbon-carbon network by employing the Grignard reagent strategy. So then you can have a longer chains carbons or longer chain functionalities in your compound by ring opening reaction. using the Grignard reagent as a nucleophilic reagent and epoxide being electrophilic center, you can prepare these sort of systems. Okay, let's move on to this example where you have a tertiary alcohol. Now you can disconnect this tertiary alcohol. You should have all the toolkits that you can disconnect this tertiary alcohol, when the one side will become aldehyde and the other side will become Grignard reagent, and in the next step you react aldehyde with Grignard reagent to give you this product. But if you want to go further, then you do FGI of this aldehyde, convert this aldehyde into alcohol, and now you can disconnect this alcohol from this position. The one side will become magnesium bromide and other side will become formaldehyde. So you can really go down towards very simple, very cheap starting materials such as formaldehyde. So starting from this cyclopentyl bromide, you react it with magnesium in the presence of diethyl ether to generate a Grignard reagent that will react with this formaldehyde to give you the alcohol in good yield. And then you can react this, oxidize this controlled oxidation, not to go towards acidic composition or over oxidation of alcohol. You stop this oxidation at aldehyde stage, and then you react this aldehyde with Grignard reagent to give you the target compound in excellent yield. So this is how you can use these strategies to do disconnection where you have an alcohol functional group. Okay, let's move on to the next example. Now this is very simple, but this is very tricky. Okay, now you have the vinyl alkyl halide where you have a alkyl halide like bromide and alkene. So what you do is you disconnect the bromine and you will get a allyl sort of cation, and then you can convert this bromine into alcohol. Either you will get B or C. So if you get C, now you have a tertiary alcohol. You disconnect it from this position and the one side becomes ketone and another side becomes alkene, having a negative charge. So alkenes are not that much acidic, as you know that. So what you need to do is to do FGI to convert alkenes into alkynes. Then you can use alkynes as a starting point, because alkynes can act as a nucleophile, as we know that, because any strong base can deprotonate the acidic hydrogen of ethine and generate a negative charge on it, which will take on the electrophilic center, in case this example acetone, to give you the tertiary alcohol. Now what you can do is FGI, like do the reduction of this triple bond using H2PDC barium sulfate Poisson catalyst to generate your desired E-alkene. Okay, I'm not going to use it at this moment. To generate the alkene, then HBr, react this compound with HBr to generate your target molecule. So the retrosynthesis was little off the beat, but if you can see the synthesis, that makes more sense, you know. And from the synthesis you can see that route C, the reagent C, is more ideal than reagent B. So instead of converting the bromide to alcohol, you are converting alkene to alcohol and bromine into alkene. And this is how you can go towards synthesis. And it's not necessary that you must follow the same route as you did disconnection. You know, disconnection could be slightly different than the synthetic route. So the forward route could be slightly different than the backward route, and it's fine. There's no issue in that. Okay, let's go on to the next example where you have this acetal linkage. Then you can disconnect this acetal. This is a CC, the CO bond disconnection. Acetal is basically a protecting functional group for aldehyde and ketones. So you disconnect these twice, CO bond, and the one part will become ketone and the other part will become alcohol. So these diols will react with this ketone to give you this acetal. Now next step is you have a vinyl sort of alcohol, and you can disconnect this from CC bond disconnection. The two sides of alcohol will become formaldehyde and the alkene will be converted into alkyne. Okay, this is the retrosynthesis. Now the synthesis will start with generation of this alkyne. What is that? Is that you use a base that will deprotonate this proton and it will generate a negative charge, and that negative charge will take on this formaldehyde to give you this alcohol in first case, and second case will be symmetrical. You will use a base to deprotonate another acidic hydrogen that will react with this formaldehyde to give you this alcohol. Now next example is, next stage is you do reduction of the triple bond using this catalyst, and you convert alkene and alkyne into alkene, and then you can react this double bond with these diols with this ketone, and now these diols will react with this ketone to generate the acetal linkage, and that will be your target compound. And this was the example where you can use this strategy for generation of this acetal formation. And this was another example that you can unmask the compounds, or you can unmask the linkages that will give you clue that how you can do disconnections having alcohols. Okay, let's move on to the next example. You have this alkene, it's a cyclic alkene, so you could either go via alcohol strategy or DiolsAlder strategy. Either is fine. I mean, it's very simple, no need to spend time more here, as it's clear. That's not much difficult, you know. And you have this alkene, and this is alkene which is substituted alkene. Now you can go through either A or C route or B, D route. Okay, so I think this synthesis will tell you that which route is better. So this one I think is better. You are generating Grignard reagent first, and then you are reacting this with acetone, and then you are reacting that acetone with H3PO4. That is the dehydrating agent. So you are doing elimination here of alcohols. You are generating the double bond. So as you know that from alcohols we can prepare alkenes. So in this step we are doing dehydration of alcohols using the strong acid to generate alkene. So strategy route BD, route B is more favorable. So B disconnection is more favorable. And this is the target molecule. And now next move on to this example. You can disconnect from this position. That will be ketone, and then you will have this ylide. So basically this is a Wittig type Wittig reaction. Then you can prepare alkenes using Wittig reaction. So this example where you have two alkenes, you can use the DiolsAlder strategy and Wittig reaction strategy to prepare this kind of functional group. So you disconnect via route B, you will get this compound, and you will get this ylide, not ylide but phosphorus containing positive charge, that can be used to generate ylide, and ylide can act as a nucleophile to take on the aldehyde. and this is your simple starting compound. What you need to do is to do disconnection of the cyclic ring, where you have 1,3-diene. You are reacting this with ene to get the product, and then you are reacting this alkyl halide with phosphorus, triphosphorus phenylphosphine, and then you will generate ylide that will react with this compound that it contains aldehyde E, and then you will get the target molecule. So this is how you can use those both strategies. For the preparation of these functional groups, where you have two alkenes, one is cyclic and one is acyclic, you can use this strategy to prepare this functionality. So this is a target molecule. Okay, let's move on to the next strategy, that is disconnection of aryl ketones. So you can prepare aryl ketones via Friedel-Crafts acylation. So you disconnect CC bond and then you reconnect it by using acid chloride as a starting materials, or its electrophilic center, and then this benzene as a nucleophilic center. This is for the disconnection of aryl ketones. Let's move on to next example. This is alcohol, but next to that alcohol is carbonyl compound, so you don't need to worry about it. But there's a trick here when you will do synthesis. The retrosynthesis is very much straightforward, but if you do not think, then you might end up with a problem instead of solution. So you disconnect these phenyl rings, okay, then you get the ester. This is fine. Retrosynthesis is okay. Now what you need to do is, instead of going this route, which will cause problems. Why? Because if you react this compound with phenyl magnesium bromide, that will react with this ketone first and ester later, okay, because Grignard reagent prefers to react with ketone first, then with ester. Now if you protect these things, like if you use protecting group strategy, the protecting group for ketones is acetal formation. You first protect this ketone, now then you react with phenyl magnesium bromide. The protected ketone will not be affected by Grignard reagent. It is stable towards Grignard reagent. Acetals are stable, they are not deprotected when we react them with Grignard reagent, and then you deprotect it in the acidic media to get the target molecule. So this was a slightly tricky synthesis compared to the retrosynthesis. Retrosynthesis was pretty much straightforward, but the synthetic route is pretty much having the trick of acetal protection on the ketone side. Okay, let's move on to the next example. Okay, this is some sort of a strategy that you will see in the next subsequent slides. In order to go there, first we need to know how we can use this approach. What is this? Basically it is alkylation of the active methylene compounds. What are the active methylene compounds? Those compounds which contain active hydrogens, or labile hydrogens, or acidic hydrogens. How we can know that which hydrogens are acidic? Those hydrogens are acidic that are in between two electron withdrawing groups. What are electron withdrawing groups? Ketone and ester are two electron withdrawing groups, and in between these electron withdrawing groups there is a CH2 unit which contains two hydrogens, and those two hydrogens are called active hydrogens. Labile hydrogens are that sort of functionality is called active methylene unit. So what you can do now, you can use this active methylene strategy by using a base that will deprotonate this acidic hydrogen and will attack on the alkylating reagent such as this alkyl halide to give you this CC bond formation. That is called alkylation of alpha position, because these are also called alpha hydrogens. What are alpha hydrogens? Those hydrogens which are next to the carbonyl compound. Okay, so how this is mechanistically works, this base picks this proton, generates a negative charge which is resonance stabilized, and this negative charge reverts back and this double bond shifts in this position. This bond goes there. These are the canonical forms, and then you can use this strategy to alkylate the alpha position. So this is the product, alkylated product. Now next thing that you can do with this functionality, you can remove this ester if you don't need it, because sometimes in synthesis you have to add this ester functional group deliberately to generate the active methylene unit, and then you don't need it at the end of the reaction because that is not what looking for. And then you can remove this ester functional group by using this strategy. In here how it is removed, that first you treat this ester either with acid or base, and then that will convert this ester into acid, carboxylic acid. Now decarboxylation is a quite common reaction. Decarboxylation means removal of carbonyl group. So you can remove this CO2 group from this acid, and then you generate this enol, which is tautomerizes into keto form. So as you know that enol, keto enol are tautomeric forms. And this is your product. Now you can see that in the final product you don't have the ester, because in this product you have the ester, but if you don't need it you can delete the ester or you can eliminate ester by using this approach. Okay, let's move on to the next example. This is carboxylic acid at the side chain and we have an alkene inside the ring. So obvious question, obvious strategy that comes to our mind is we can use the Grignard reagent approach, or we can use the DiolsAlder reaction strategy for inside alkene. Inside alkene means the double bond inside the ring. Okay, what you can now do is you can disconnect the CC bond, and then you will end up with alkyl halide on one side and negative charge on the CH2 unit. Now there you will need active methylene unit. You deliberately add an extra ester to make this CH2 unit most active or most acidic. Then you convert this bromine into alcohol, that's FGI. Then you convert alcohol into ester, that's another FGI step. So couple of FGI steps. Now what you need to do is to do the DiolsAlder reaction at the last stage, and in the last step of retrosynthesis becomes the first step of synthesis. This is basic, you know. When you do retrosynthesis, your last step of retrosynthesis becomes the first step of synthesis. So the retrosynthesis of this ester having alkene inside the ring was the last step. So in synthesis it becomes the first step. You react this 1,3-butadiene with ene to generate this compound, and in the next step you reduce this ester with lithium aluminum hydride into alcohol, because alcohol ester can be reduced into alcohols, and then you react this with PBr3. The alcohol is converted into alkyl halide, and now you are reacting this alkyl halide with active methylene unit using ethoxide base ethanol solvent. You get these disubstituted esters, like a couple of esters there. Now what you need to do is delete one ester completely and convert one ester into acid. What you do, ester hydrolysis, that will convert this ester into carboxylic acid. That's what we need. And in the next step 2, you delete this ester by heating and decarboxylation strategy to get the desired product. So this was the example where we used this active methylene strategy to generate the nucleophile which attacked on this alkyl halide. And this is how you can tackle when you have acid and alkene in the same functionality. Okay, let's move on to the next example. Now you have ketone and alkene in one compound. What you will do? First you will do FGI to convert alkene into alkyne, and then you can disconnect this methyl group, that is called alkylation of alkynes. Because alkynes are acidic, we can generate a negative charge there. They can attack on the electrophilic site alkyl halide to generate this compound. And next again we do alkylation There we can disconnect this CC bond, and one side becomes actylmethylene, the another side becomes the alkyl halide part. Now you have this actylmethylene unit here in synthesis. You are reacting this with a base. That base will generate a negative charge there, and that negative charge will attack on this alkyl halide. In this case it's not alkyl, but it's alkenyl or triple bond containing alkyl halide, triple bond containing halide like bromide. That negative charge will attack on this carbon, which is sp3. It will undergo SN2 reaction to give you this alkyl product. And in the next step, what we are doing is protecting this ketone and by acetal strategy. And in the next step, what you are doing is alkylation of this alkyne. And in the next step, you are removing this protecting group using HCl and H2O, because acetals can be deprotected or can be removed in the acidic conditions. So all you need is HCl and water to remove this acetal. And in the next and the final step, you can convert this alkyne into alkene using H2PDC barium sulfate catalyst. So this is how you can use this retrosynthetic analysis to reach to a target molecule. Let's move on to the next example. That's example 61. You have simple ketone, you FGI ketone into alcohol, and then you do Grignard reagent strategy. And there is one more important tip in this slide, that acid chlorides are most reactive and amides are most stable. So this is the reactivity and stability order, and reactivity and stability order goes against each other. The most reactive becomes the least stable, and the most stable becomes the least reactive. So stability and reactivity are inversely related to each other, and this is the order of stability and order of reactivity. And the acid chlorides are most reactive, hence they will be least stable. Amides are most stable, hence they will be least reactive. We are just talking about the carboxylic acid derivatives, their stability and reactivity. Okay, let's move on to the next example, because in this reactivity and stability will help you when you have a chemoselectivity issues in compounds. Okay, this is a chart that shows you how you can interconvert functional groups. So if you have an acid chloride, if you react this acid chloride with alcohol, you generate ester, and if you react with this ester with amine, you generate amide. Now you can convert this acid chloride into acid anhydride, esters, and then amides, and you can prepare carboxylic acid using, if you react Grignard reagent with carbon dioxide, you can prepare carboxylic acid. And if you do hydrolysis of amides, you can prepare carboxylic acids. If you do hydrolysis of esters, you can prepare carboxylic acids. If you do hydrolysis of acid anhydrides, you can prepare carboxylic acids. And if you do hydrolysis of this acid chloride, you can prepare carboxylic acids. And you can prepare acid chlorides from carboxylic acids by using thionyl chloride or phosphorus pentachloride. So this was a interconversion or reactivity of carboxylic acids and their derivatives. Okay, let's move on to the next slide. Now you have this amide functional group. In order you want to disconnect this compound, so you can disconnect from this position, that is called a CN disconnection. And this CN disconnection is basic disconnection where you can disconnect into two fragments. The one fragment becomes the amine and second fragment becomes the carboxylic acid. Sorry, I have to sip water. I'm feeling thirsty. Now you convert this acid into Grignard reagent. As you know that carboxylic acids can be prepared from Grignard reagent and carbon dioxide, and then you can do FGI of this Grignard. You convert this Grignard reagent into alcohol, and then you can do the CC bond disconnection, and one side become alcohol, so one side become aldehyde and another side becomes Grignard reagent. In the forward synthesis, you can react this alkyl halide to prepare Grignard reagent. And Grignard reagent can be prepared by reacting alkyl halide with magnesium diethyl ether. That will react with ethyl aldehyde to generate alcohol, and that will then, in the next step, you will react alcohol with PBr3 to convert alcohol into alkyl halide, and then you will convert bromine and react with this bromine with magnesium and diethyl ether to generate Grignard reagent, this one. And then in the next step, you will react this Grignard reagent with this carbon dioxide to generate this carboxylic acid, and in the next step you will convert carboxylic acid into acid chloride using thionyl chloride strategy, and in the last step you will react this acid chloride with secondary amine to generate the amide linkage. So this is how you can use this functional group interconversion strategies to generate these amide functionality. Okay, let's move on to the next. Okay, this is simple alkane, R1 and R2. You can do FGI of alkanes into alkenes, and then you do the Wittig reaction for alkenes, or you can use the Grignard reagent approach for alkenes. For Grignard, you need to convert alkenes into alcohols, and then you can go from alcohols to Grignard reagent. For example, if you have this simple compound which does not contain any functional group, how will you do retrosynthesis? It may look simple to you, but it's not. You need to have a strategy. What you will do FGI. You convert one of this simple alkane type chain into alkene, and then you will disconnect this double bond of alkene, and the one side will become Grignard. This is a Wittig reaction. Then this Wittig ylide will react with aldehyde to give you this alkene. So how these ylides are prepared? They are prepared like Grignard reagent from alkyl halides. So you react these alkyl halides with triphenylphosphine and a base to generate ylide. That ylide will react with aldehyde or ketone to give you the alkene, and then you can reduce alkene into alkanes. So this is how you can use this. Okay, let's move on to the next example. You have this compound which is target molecule 71, and I'm using the Stuart Warren workbook, so I'm trying to explain from that book. Okay, you have the cyclic alkane now instead of state chain alkane. Now what is here is cyclic alkane, cycloalkane. You do FGI, you convert the cycloalkane into alkene, and then you do FGI to convert alkene into alcohol, and then you do Grignard reagent approach because this is tertiary alcohol. So you can prepare this alcohol, tertiary alcohol, by reacting phenyl magnesium bromide with cyclohexanone. So first you have to prepare Grignard reagents. So you will start from phenyl bromide, and that will react with magnesium in the presence of diethyl ether to generate Grignard reagent, and that Grignard reagent will react with this cyclohexanone to generate tertiary alcohol, and then you do the dehydration of this alcohol to generate this cyclohexene double bond inside the ring, and then you reduce this double bond with H2PDC to give you this target molecule. Okay, hope you understood this example. Let's move on to the next. So this is not an example, but it's a summary that how you can do disconnection of different functional groups, summarizing the whole what we have learned so far in this video. So you can use alcohols, disconnect alcohols from this position CR, and you can disconnect alkenes from this position, that is Wittig reaction. So these are the question mark that I'm asking from you to answer me in the comment section, because you have already learned in this video that if we disconnect R1, what will be here? If we disconnect from this position, what will be here? Name needed, like Wittig reaction or something that you think that will go there. So it's kind of a mini exercise for you guys to do it, and the answers are also there in this slide. So all you need is to learn this. So if you disconnect this R1, that will become Grignard reagent, and the other compound will become ketone. If you disconnect from alkene from this position, one side will become phosphorus containing elite, and other side will become ketone. That is called Wittig reaction. And then you have carboxylic acids. You can disconnect the R side chain of this carboxylic acid, that will become Grignard reagent, and carboxylic acid, carbon dioxide. As you know that carboxylic acids can be prepared from Grignard reagent. And then you have this compound. Then you have carbonyl compounds, this one. So this is ARYL ketones. You can do Friedel-Crafts acylation and alkylation of the acidic hydrogen. You can use this active methylene strategy. Okay, I hope you liked this video so far, and I'll stop here and then I'll continue from there in the next video lecture. This was the last slide for the summary of what we have done so far. And if you have any questions regarding retrosynthesis, please ask in the comment section. But if you have first go and watch my previous videos about retrosynthesis. That might help you to answer your questions before putting comments in this video. And I'll continue to make a couple of more videos about this retrosynthesis, longer videos like this one. And I'll use the Stuart Warren retrosynthesis workbook and simple book to give you more examples that you can do practice, and you can learn how simple changes in the structure can give you a difficulty in retrosynthesis and synthesis, and how you can use the protecting group strategy, functional group interconversion approach, and other strategies for retrosynthesis and synthesis of all sort of compounds. So if you are really cool, want to become master at retrosynthesis, please follow my videos, and I hope to see you with next video about retrosynthesis, another one that will be longish video. Sorry for making the long videos, because I believe that doing many videos of short videos of retrosynthesis may not help you, some of you, but what I will do is, first I'll make long videos. So if you want to learn in one video, then you can go on and watch one long video and learn all of the examples. And if time permits, then I will make short videos about retrosynthesis, where I will pick most difficult examples or most complex examples and do retrosynthesis of those complex compounds in short videos, so that you can know the answer so very quickly, depending upon the knowledge that you have about organic mechanism, organic synthesis. So the last thing that I would say, that if you want to be good at organic chemistry, you should be good at organic synthesis, and then organic synthesis demands that you must be good at mechanism, reagents, synthesis, and retrosynthesis. So hope you guys are getting benefit from these videos, and we will continue this retrosynthesis lecture series with more long videos. And thanks for watching. See you. Bye.